Okay guys, the idea of this video is to show the implementation of problem 9168 that we just solved by hand in EES. As we mentioned in our class, the first thing will be, and it's just a housekeeping, in the diagram window to have the text, copy the text of the problem. That helps you to understand what are you solving, and by reading later on the program and the diagram that you have here, you will understand what you are saying. Okay, so the process we are going to be following is pretty much the same as we did in the analysis. First, we're going to add the relationships, and then we're going to put them in comments, because since we don't have all the information, every time that we try to check, it will create an error because we're lacking some information. So basically, once that we define that, and noting that first we did it by hand, we know that it works, and we're going to start computing each state. We are also going to check the system units. We know that we're going to be working in Kelvin, so that's marked. The rest is international system. It's okay. So first of all, we are going to add our general relation. This is the first law analysis that we have. You can see that we have the relation for the work of the turbine, work of the compressor, work the Q in and Q out, the network, total heat in, the real efficiency of the backward ratio. If we press F2 at this point of time, we're going to get an error because all of these variables are not defined yet. We have 10 equations and 19 variables, so how do I get them? Well, the way we're going to do it is we're going to put them in comments. And put them at the end. So now when we press F2, we are not going to have any result. So basically, we don't have equations. The only result that we have is H1, because that's the initial value. Okay. So now we're going to start by adding each of the states. Recall that to introduce each state, you can use this function, thermal-physical function, ideal gas, air, and for instance, we're going to have enthalpy. Enthalpy is only a function of temperature. And notice that we are using square brackets that will create an array that let us at the end plot it against the property table, the property plot if we want. So I will add this. Sorry. So if I press F2, I have one equation with two variables. And I have this error. So I need to find out, I will define T1 since I know it from the program. (300 Kelvin). If I press F2, I can see in my array table these values. I'm going to convert this way. And we're going to keep working this same way for each of the properties. So state 1 will look like this. Notice that, of course, I put at the top in comments this the name of the problem as well as the number of state. and I have pressure, temperature, and enthalpy and entropy. I don't have PR in this case because PR is a way, that table is a way of analyzing isentropic states, isentropic processes. In EES, what we can do is find out entropy and then define the process to be isentropic. The way of defining this process to be isentropic is something like this. S2 equal S1. Notice that S2 is without brackets because this will be the isentropic state. And I am not interested in plotting the isentropic state but the actual state. So this is the way I am creating. Here I am defining the isentropic process and I can make a note for me to remember later on. This is the isentropic process. I can define P1 and P2. If you notice, I need to know P2, P4 in advance. If I press F2, I am missing one of the variables. When I say yes, P4 is one of the variables that I am missing. But this is the way that we are going to define my isentropic process. If I can put a pressure 4 here, then I can solve it. I am getting a little bit ahead of me, but I say, okay, I know P4 is one of my one of the data that I have for entry, so I already put it here. And if I press F2, it can be solved. And if I press this icon, it goes to my array table. This is my matrix of data. You can see that now I have temperature, enthalpy, pressure, and entropy. It's fully defined for state 1, partially defined for state 2 and 4, and it's empty for state 3. It doesn't matter because I can solve it for these numbers. What I cannot solve or what I have not defined is blank. Okay? So we know we already get state 2s, and we need to define state 2 actual, and we do that with the isentropic efficiency of the compressor. This way, I define the isentropic efficiency of the compressor to be 0.8, find the equation, and then how do I compute H2 and S2? Notice that in this case, P2 is the same because it's the compression goes between these two pressures. Temperature is not the same. I need the enthalpy to compute the temperature, and the temperature and the pressure to compute the entropy. This could be difficult to read because you have parentheses and operation signs. So if you want to check, let's say I want to check if it's well written, I can press in formatted equations or F10, and I have it the way I will write it. Right? So I check that it's effectively it's H2S minus H1 by H2A. This is the way it shows when it's brackets minus H1. So I am okay. If I press F2, it should solve it. And if I go my array table, I notice that state 2 is completely defined. Since state 3 is already defined, I will just copy this is state 1 and change whatever is needed to define state. Finding that pressure 3 and pressure 2 is the same, I know from the problem the temperature 3, and I define enthalpy 3 and 4. Now, state 4s and state 4a will be pretty similar to state 2s and 2a. I only need to take care of defining that this is the efficiency of compressor 2, even though it's the same value. And that let me, in the future, change one independent of the other. Here I fully defined state for S. Again, this part is the isentropic. I am defining here the isentropic process. I need to put marks. So I can check it later on if I want. Find the temperature for S, that the isentropic temperature, and the enthalpy for S, that the isentropic enthalpy. And defining again the isentropic efficiency of the second compressor, and its relation I can solve for enthalpy and entropy. I press F2. Notice that I have a solution here, and my array table is complete now. I will change this order a little bit so I can have temperature, pressure, and then the dependent variables, enthalpy and entropy. Okay, now it comes a tricky part. When we did the analysis by hand, we said that we need to skip at initially state 5, because we need state 9 to get it. But if you notice, what we're doing is every time that we compute one state, we solve it to see that there's no problem. That is a good approach. You don't want to work 2 hours, have a lengthy code, and then try to debug it, finding out that you have a lot of typos. So this will be a better way of proceeding. Capture one state, solve it, see that there's no problem, that you don't have any initial guesses that you need to check, and so you know that right now you are okay from state 1 up to state 4S for actual. So what we're going to do is we're going to assume a value of 5, temperature 5. We know temperature 5 should be higher than temperature 4, but lower than temperature 6 after the combustion. So we're going to choose any value in the middle, and we're going to use it just to compute H5. Later on, we're going to delete that, introduce the effectiveness equation, and that will solve, that will close our systems of equations. So this value of 800 is just an initial guess, and I am making this note here. This is a guess value. We're going to comment this once we introduce the generator. When we said to comment, is that we are going to put it in comments, just like we are doing with the epsilon expression. And I will make a note here. Once we close. No, I will not make any note. So, but basically, this value is just for the process to keep going. I don't need H5 at this point of time, but I will need it later on. So I just want to keep rolling. And if I press F2, I notice that I have up to state 5, right? Now, I will keep going and introduce state 6. State 6, we have the same pressure as the pressure 5, and we know that it's 1400. So we need only to compute enthalpy and entropy. Recall that process 6 to 7 is isentropic, so I will do exactly the same thing as I did in the compressor. I will first find the state 7S, and then using the definition of isentropic efficiency of the turbine this time, I will find out the actual values of entropy and enthalpy for state 7. You can see here that I defined state 7S, and I defined so A. The difference is that we have now the isentropic efficiency of the turbine. If I press formatted equations, you can see that the definition of isentropic efficiency of the turbine is occurring with what we have in our video. So if I press F2 or I solve it, notice that I have this data, and my table now grows up to state 7. We're going to do the same thing for state 8, which is the definition of the inlet of the second turbine, state 9S and 9A. Since right now it's a little bit repetitive. Now you can see that we have state 8, 9, 9A, 9S and 9A, and if we press F2, we're going to solve everything. These values are the 9 values that we have. Recall that stage 5 we invented. If I change anything here, state 5 instead of being 800, I said is 850, I would change it just to 50 degrees. It will work the same, right? Now, I know that state 5 depends on state 9 and the relation is this epsilon. So I will take the comments here out and I will make a comment of this. If this is a problem, we'll say, okay, I don't know, I need to compute H5 using the definition of epsilon, and then I will use this H5 to compute temperature 5 and entropy 5. Recall that this doesn't require that you have this previously, because it will be by iteration. So if I press F2, I'll have the value of T5. You can see that it's solved, and you can see that it's 907. We say it should be higher than temperature 4, lower than temperature 6. So now we have all of our data, all of our states. So finally, what we can do is just to move these comments and press F2. And we notice that we have our background ratio and our network that are the same as we have in the hand solution. And by the way, the thermal efficiency is always the same that we have in the solution, different from what we have in the book. So we're going to assume that we are right. We have two different methods getting the same result. Okay, so finally, what we're going to do is we're going to plot this in a diagram. We're going to plot property plot. We would like to plot ideal gas, air, and let's do a TS diagram. In a TS diagram, I will choose 3 different pressures to show. One is 100 kilopascal, the other one is 1400 kilopascal, and one of the pressures I would like to be 400 to 446, which is the value that I have for pressure 3, right? I plot it, and this is my data. The black ones are pressures. Now I would like to overlay my cycle, and I will take this from the array table. And I have temperature on the y-axis and entropy on the x-axis. And I will make the symbol, and I will use a black line. I will use red. Automatic update if I change something, and I will add a legit item so I know what it is. And I will add the point labels. Okay, so it's okay, and I have my cycle. Notice that these lines are not vertical because I don't have isentropic process, but I have actual processes. Finally, I'm going to show you how to create a parametric table. Okay, parametric table will be a table in which I will change one parameter. We say that P2, the extract pressure, will change the work output and have also the efficiency. And we choose this number to be this number to be the optimum. So we're going to find out if that's true. And one way of doing is to have some visual indication. Since the value that we're going to change is P2, we're going to make this a comment. By doing this, we don't have P2, right? If I press F2, it's undetermined, and one of the values, of course, is P2. The way we're going to solve this is to create a table. So in the table, we'll create a new parametric table. I will ask it to have, let's say, 20 runs. The first value that I want to check is P2, the pressure. And I would like to understand the influence of P2 on the efficiency. If I don't want to scroll along all these array tables, I press here and say, okay, I like to take the efficiency and the network, because we said that they are not necessarily the same values, the same optimum. Okay. If I press this, it creates a table. Now what I'm going to need to do is to assign values. And I know that P2 should be higher than 100 Pascal and lower than 1200 kilopascal. So I will say I don't want to think a lot, so I will say I would like to change it from 200 to 1000, and it will change linearly. It creates this table, and now if I press F2, I still have the same problem. But if I press this F3 solve table, what it will do is for every run, it will say, okay, what is the value of P2? 200. Next run, 242. Solve everything and only have here my values of thermal efficiency and network. I press F3. I have the results. So I have solved. I know the relation, but it's difficult to read. So instead of trying to read, I will create a plot. Plots are very useful to get insight. New plot. I want an X, Y, and I will create P versus the efficiency. I will create an automatic update if I change anything. Spline. Make a smoother line. I will add the legend, and I would like to have this symbol for the efficiency. I notice that I have a maximum and then it goes down. But I would like to have in the same plot information for the network. So again, plot, overlay plot, because I'm going to plot on top of this one. This time I would like to have the network. Notice that I have different scales. Here I have decimals, here I have hundreds. So I'll say use please the right scale. Spline, automatic update, add legend item, and this time I would like to use this symbol. Notice that the maximum are not on the same point. And if I add grid lines, if I press right click, I press double click, I can add where do I add grid lines? Hold on. Okay, we can do that later. But you can see that we have 200, 400, about 380, so it's very close to the value that I want. If I want to get the exact value for the optimum, I can run calculate and say I would like to have minimum or maximum. and I would like to optimize for network, and I have just one variable because I have one comment, so I will choose P2. I'll give it some bounds. Say I would like to have lower to be 100, 200, and 1000. And we have initial guess of same value that I have. I will use 800. Okay, and if I it's okay, I notice that it's 359.7. Okay, guys, I hope this. If I press continue, I will have the solution for that specific value. Okay, guys, I hope this helps. We're gonna keep working with EES. Thank you very much.